All right, hello everyone, and welcome to the last video of Unit 6. Today we are going through 6.8, which is on enthalpy of formation, as well as 6.9, which is on Hess's law. Your learning objective for 6.8 is to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. And your essential knowledge is that tables of standard enthalpies of formation can be used to calculate the standard enthalpies of reactions. And the equation for this lesson is delta H of your reaction is equal to the sum of the delta H of formation of your products minus the sum of delta H of formation of your reactants. So in lesson 6.7, we were doing reactants minus products. In 6.8, we are doing products minus reactants using different types of values. So standard enthalpy of formation, which is written as delta H with a subscript of F, is the energy change when 1 mole of a compound is made from its elements in their most stable form at standard conditions. So in simple terms, it tells us how much energy it takes to build a compound from scratch. If the value is negative, energy was released when that compound was formed. If it's positive, then energy had to be absorbed in order to make that compound. Two very important things to remember for this lesson is first, any pure element in its normal state has a delta H of formation of 0. So something like O2 or solid carbon, because those elements are in their most stable form, they're going to be our starting energy baseline, and they're going to start out at 0 for delta H of formation. The second important note is that this method is going to use products minus reactants, which is very different from bond enthalpies where we did reactants minus products. Just know that they are two different ways of essentially bookkeeping the energy. You just need to pay attention to which method the problem is asking for. Both of these methods are ways to calculate delta H of the reaction. They just look at energy from different perspectives. So with enthalpy of formation, which is this unit, all the energy of the bonds is already built into the values in the table. So each substance has been measured relative to its elements. So we simply compare where we end to where we start. And that's why the formula is products minus reactants. It's final energy minus initial energy. Now with bond enthalpies, which is what we learned last lesson, we pretend to take the reaction apart ourselves. So first we add up the energy needed to break all the bonds in the reactants, and then we subtract the energy released when we form new bonds in the products. That's why the formula is bonds broken minus bonds formed. So to calculate the enthalpy change for an entire reaction, we can use the standard enthalpy of formation for your reactants and products in the equation above. Just make sure that we are using a balanced chemical equation because that's going to tell us our stoichiometric values to use when calculating. So let's look at this practice problem below. We have 2C4H10 reacting with 13O2 to form 8 CO2 and 10 H2Os. And it says to use standard enthalpies of formation to find delta H of the reaction. So first I want you to take note that we have O2 here. And remember O2, we are going to have an enthalpy of formation of 0 because that is our baseline since it's in its most stable state as an element. So that is not going to have an enthalpy of formation value. So looking at everything else besides the O2, we know we are solving for delta H of the reaction. So we need to first add up all of the delta H of our products. So we have 8 carbon dioxides. Carbon dioxide is negative 393.5, so we're going to be multiplying that by 8. And then we have 10 water, so we're going to take this value and multiply that by 10. So that's going to give you negative 2,418 kilojoules per mole for water and negative 3,148 kilojoules per mole for carbon dioxide. So when we add those up, which is all of our products, that's going to give us a value of negative 5,566 kilojoules per mole. So we're doing products minus our reactants. So now we're going to get C4H10. And since we only have 2 of those, we're going to multiply this value by 2. Which gives us negative 294.6 kilojoules per mole for C4H10. So that is our reactant, so that's going here. And now we can solve for our delta H of the reaction. And that gives us a final value of negative 5,271.4 kilojoules per mole. And then with the correct number of sig figs, this would be our final answer. All right, so let's do another practice problem. It says use standard enthalpies of formation to find the delta H of reaction for the following reaction. So here we have another combustion problem. Again, O2 that is in its elemental pure form, so it's going to have a formation of 0. So we're just going to kind of ignore that when we're doing our math. When we are solving for this delta H of reaction with our enthalpies of formation, remember it's products minus reactants. So we have 1 carbon dioxide, so that is negative 393.5 plus our 2 waters. It's going to be 2 times our water, which is negative 241.8. So that is our products, and then we're going to subtract our reactants, and we just have CH4, so that's going to be negative 74.8. So our final answer for the reaction would be negative 802 kilojoules per mole. All right, so let's do one more example problem before we move on to Hess's law. This says the enthalpy change for the reaction is negative 860 kilojoules per mole. Based on the standard enthalpies of formation, what is the approximate delta H of formation for Fe2O3? So we have the total delta H for the reaction, which is our negative 860 kilojoules per mole. We also have the other components within our reaction. We're just missing Fe2O3. So we know delta H of the reaction is equal to negative 860. And we know we do not have our reactant, but however, we do have our product. So our product is negative 1680, and that's going to be minus our reactant, which is Fe2O3. So that's what we're solving for. So now in order to solve for that, we're going to add over our 1680 and then change the sign because there's a negative in front of Fe2O3. So Fe2O3 is going to be negative 860 plus 1680, which is going to give us 820, and then we're going to change the sign because there is a negative in front of Fe2O3. So that's going to give us negative 820 kilojoules per mole for our standard enthalpy of formation of Fe2O3. Right, and then moving into Hess's law, we did a good chunk of Hess's law on our Unit 6 introductory packet. So if you have not watched that video yet or gone through the packet, I highly recommend doing that. Hess's law essentially tells us that a chemical or physical process can be broken down into a series of smaller steps, and the total enthalpy change of the overall process is equal to the sum of the enthalpy changes of each step. So this works because we have conserved energy. So no matter what pathway a reaction takes, the overall energy change from reactants to products is going to be the same. Now, Hess's law tells us that the enthalpy change of a reaction does not depend on the path. It only depends on the starting materials and the final products. So in this diagram, route 1 shows the reaction happening in one step. So we're going from the reactants right to the products. Route 2 shows the same overall change happening, but it's happening in 2 steps through an intermediate. So we're going to have energy changes as delta H1 and delta H2. Hess's law is just saying that these 2 steps must be equal. So our direct path, delta H of a reaction, is the same as our alternate path, which is delta H1 plus delta H2. So they're just equal to each other as shown here. To use Hess's law with multiple reactions, which is probably the most common application of this, we're going to rearrange and combine known balance equations to match the reaction we want. So if we flip an equation, we're also going to flip the sign of delta H. If we multiply an equation, we're also going to multiply delta H. If we divide an equation, we're going to divide delta H, and so on and so forth. So if you manipulate the equation, you're also manipulating delta H. So let's do an example of that. We are looking for that top equation there, but we are given our standard enthalpy changes for the reactions 1, 2, and 3 below. So we're going to try to match that top one. So I like to start in order. It's kind of up to you how you want to do it. But I see I have 2 carbons here as reactants. So I just want to make sure my carbons are reactants, which they are. But I need 2 of them. So I am multiplying this entire equation by 2, which means I'm also multiplying my delta H by 2. And that will give me 2 carbons. So for reaction 1, my new equation is 2 carbon plus 2 H2Os reacts to form 2 COs and 2 H2s. Then I'm going to move on to my water. So my water, I have 2 waters as reactants. As you can see, I have a lot of waters happening, 1 in each equation. So I'm actually going to move on from that because typically they handle themselves without me manipulating. So let's move on to CH4. So CH4, I have 1 CH4 as a product. And as you can see, CH4 is down in our 3rd reaction, but it's a reactant. So we're going to flip this equation, which means we're also going to flip the sign of this delta H value. So 3 will now be 3H2 plus CO reacts to form CH4 plus H2O. And then finally, I'm going to look at CO2, my last substance. It is a product, and there's only 1 of them. And as we can see in step 2, it is a product, and there's only 1 of them. So step 2 is most likely going to stay the same. So now that we have that figured out, let's go ahead and make sure that everything cancels out the way we want it in terms of the waters. So looking at our 3 equations here, I can see that my carbon monoxide is gone. So I have 2 carbon monoxides on the right. I have 2 carbon monoxides on the left. For my waters, I have 2 waters as reactants in the first equation, but I also have a water as a reactant and a product in the bottom 2 equations. So I'm going to cancel those out, and I'm left with 2. And then finally my H2s. So I have 3 H2s on the left, and I also have 3 H2s on the right. So I'm left with 2C plus 2 H2O reacts to form CH4 plus CO2, which is in fact our equation. So now that I've double checked that those are correct, I'm going to go ahead and add up all of my enthalpy values with the change. So my first one is going to be 131.3 times 2. So that's going to give me positive 262.6. I did not change my second equation, so that's still negative 41.2. And I did change my final one by changing the sign, so negative 206.1. So I'm going to add all those together. 0.2 minus 206.1. That's going to give me an overall delta H of reaction of positive 15.3 kilojoules. And that will be my final answer. All right, let's do one more of those just to make sure we are good to go with Hess's law. So we are given that top equation there, and it says to determine the enthalpy change of the reaction. So starting with 2NO, I have 2NO already as reactants and with the same coefficient, so I do not have to move anything there. My O2, I already have O2 as a reactant with the right coefficient, so I leave it there. And then finally, N2O4, it is a product with a 1 coefficient. I do have a 1 coefficient, but it's a reactant, so I'm just going to flip this equation, which means this is now a negative sign. So now with my new equation, that would be 2NO2 reacts to form N2O4. And that's going to be a new delta H value of negative 57.9 kilojoules. So now just making sure that everything cancels out. I have 2 NOs. Those are remaining. I have an O2 that is remaining, and I have N2O4 that is remaining. My 2 NO2s are going to be gone. So that is, in fact, my equation. So I'm good. Now I'm just going to add up my enthalpy values. So I have negative 57.9 minus 113.1. That's going to give me an overall delta H of reaction of negative 171 kilojoules. All right, and that is the last unit of Unit 6. See you next unit.